Okay, hello again. This is just a video on the modulus argument form of a complex number. Okay, so the work you've been doing recently has basically argued that you can have a geometric interpretation of a complex number on something called the Argand diagram. Now, I will say a few words about that. I apologize, it will be a little bit philosophical again. We call this axis the real axis. Um, there we go. And we're going to call this axis the imaginary axis. So we'll call it M. Um, yeah, the imaginary axis is there because we couldn't put the square root of -1 anywhere on the real axis. It's got to be completely orthogonal, i.e. perpendicular to the real axis, because it shouldn't have any real components. The real component is 0. So we end up with that is I, that is 2i, that is 3i, and so on and so forth. We don't normally write the I on there low. It's normally enough to just call the axis im, and then we can just say 1, 2, and 3. And -1, -2, and -3. And the real number is real number axis is as normal, 1, 2, 3, so on and so forth. Now you're fine, I suspect. You're probably thinking though, why? You're fine with plotting complex numbers, I'm sure, on this Argand diagram. Yes, it is just like vectors, if you like. Yes, adding them is just like adding two vectors, for example. And plotting them is exactly like plotting on the Cartesian plane. It was Hamilton, actually, who liked to think of complex numbers as an ordered pair. That was in the 19th century. It's relatively recent that we've got a lot of this mathematics with complex numbers. So, it's quite nice to do it because it really is some recent mathematics. But yeah, we can describe them using like a Cartesian approach, if you like. Well, let me point out that there's another way of doing coordinates. There's the Cartesian coordinate where we do something like 2, 3, and that describes where something is relative to a common origin. But there is actually another way of doing coordinates. Yeah, instead of like let's say I'm dealing with the point 3, 1. Yeah, I could describe it using saying basically go 3 across and 1 up, but here's another way of doing coordinates, and it's much more like bearings. Yeah, you could say you need to rotate it by a certain angle, which in this case would be inverse tan of a third, which I think is about 19 degrees, isn't it? Let's have a look. Inverse tan of a third doesn't really matter. 18.4 degrees, yeah? You could instead say rotate 18.4 degrees in an anti-clockwise direction and travel, and then you'd have to state this distance here, and it's going to be root 10, and travel root 10 units, yeah? So we could instead give an angle and a distance to travel from the origin, yeah? Now, that is called, for complex numbers, we call it modulus argument form, but we actually call it polar form actually quite often, and we're gonna be dealing with polar coordinates and equations defined using polar ideas basically next year in the next book. It's fascinating when you do geometry with polar coordinates. Really interesting. Really interesting. And you can do lots of like fun stuff like spirals and cardioids and that kind of thing. But yeah, we're going to be talking about the modulus argument form here. And modulus argument form is exactly this. It's just polar form. It's just a way of describing how you get from the origin to a point on the complex plane, but using an angle and a length rather than how far you go along the real axis and how far you go along the imaginary axis. So here, this complex number, which could be written, if you like, in Cartesian form as just 3 plus I, and let's actually write that down over here. I'll write it down with a different color. So this number here, we could call 3 plus I. Let me get rid of that because that's not doing anything anymore. Okay, so 3 plus I. Now, that is, yeah, I'm going to describe it as Cartesian form, especially because Descartes was the one who came up with A plus BI. So let's call that Cartesian form. But, so I'll just write that above it. But let's do modulus argument over here. Let's do another color for modulus argument form. Okay, to describe it in modulus argument form, well, we we there's lots of ways you can write modulus argument form actually, but we write it as Cartesian form is like x plus iy. Oh, let me do this in the right color as well. X plus iy, modulus argument form. We write it like this sometimes: r cos theta plus I sine theta. Now, doesn't that look complicated? But it's not, and you can actually work out with your calculator, it works out exactly the same. Now, R is just the modulus, it's just the length of the actual distance. It's just the distance from the origin to your complex number, where it is on a complex plane. So that's going to be root 10 here, yeah? And then you're going to have cos of theta here. Now, theta is going to be inverse tan of 1 over 3, opposite over adjacent, and that equals 18.4 degrees. We don't normally work in degrees though now, we're all grown up, so let's turn that into radians. We normally work in radians, very rarely work in degrees, so let me just change my calculator to radians. Let's get grown up about it. 0.3217. And so I'm going to call this cos of 0.3217. And then plus I sine of 0.3217. Now, if you actually work that out on your calculator, like type that in without the I, but work out cos of 0.3217 times it by root 10, work out sine of 0.3217 times it by root 10, you will end up with this over here. You'll end up with 3 plus I. So they are absolutely equivalent. And that's because you can clearly see here from the work that we've done with SOHCAHTOA and mechanics and things like that, this is just going to be root 10 sine of that angle. Let me write this down. Yes, root 10 sine of theta, and that's going to be root 10 cos of theta. That's the way a right angled triangle works. The only reason we've got the I in there is because on the imaginary axis we attach the I component, don't we? So that coordinate 3, 1 becomes 3 plus I. And that is modulus argument form in a nutshell. Now, it's, it might seem weird at first. The more you stick with this, the better it gets. The more the pieces of puzzle fit together. But it does get weird. And in fact, there's a much nicer way of writing this down because. And this is what we do next year. This is what you've got to look forward to. We can actually write it down like this as just RE to the I theta. And so it's actually the same as root 10 e to the I times 0.3217. And that's a much quicker way of writing it down in modulus argument form. And it means exactly the same thing. And it's because e to the I theta, we can get into all the interesting stuff, equals cos theta plus I sine theta. And from that, it's very easy to derive the magnificent result e to the I pi plus 1 equals 0, which is called Euler's formula. Well, sometimes it's called Euler's formula. Euler's got a few formula named after him, but this is his magnificent result. Magnificent. Is it called Euler's identity, actually? Euler's identity. But yeah, it's an incredible result. As you can see there, you've got E, a special number in maths, pi, a special number in maths, I, a special number we're now learning about in maths, and 1 and 0 is a fantastic equation. Anyway, sorry, I occasionally mention that we're building up to that. That is what we're building up to. Look forward to it. Okay, so let me just try and find, let me just point out two massively important things now. And this comes up in exercise 2D. It's about when we're adding in modulus argument form, adding or subtracting in modulus. Yeah. Let me reword this to call it multiplying and dividing complex numbers in modulus argument form. Multiplying and dividing complex numbers in modulus argument form, we have some astounding results. Some really, really useful results. And you'll see why modulus argument form is popular, because things work so simply when you're using modulus argument form. So what do we have? Well, we have lots and lots of, I'm just going to write down the two facts. Like if Z1 and Z2 are two complex numbers, then the modulus, and we write down modulus using the modulus function. That's what it's about. It's about the length of the line. The modulus, or after you've multiplied two complex numbers together, is simply the modulus of one complex number multiplied by the modulus of another. That might seem like not that big a deal, but it's a massive deal. It's very important. Learn it. Learn it. It's really useful. What it basically says is if you've got two complex numbers, let's just quickly do, let's say one here and one up here, and you times them together, what we're going to need to do is times that length by that length to find the resultant, basically the result of where it's actually going to be. It's going to be coming down here somewhere, and it's going to be whatever that. Let's say that's 2 and that's 1. Well, actually, then that. Well, let's say that's 2 and that's 3. Well, 2. Let's say they're both 2. Then this is going to be length 4. Yeah, the actual length of the line. And even more interestingly, or just as interestingly, what happens to the argument? Well, I hope you're familiar now with this notation. Arg for argument, the argument of Z1 times Z2. Now this works a little bit differently. It's the argument of Z1 plus the argument of Z2. So you add the angles. If you ever multiply two complex numbers together, you add their angles. Bear in mind, the argument's always taken in the positive direction from the real axis and goes from 0 to pi on the top and 0 to minus pi on the bottom, yeah? So let's say complex numbers here. That looks to be about pi over, what is that, pi over 4, because that's pi over 2 right here. Whereas if one was over there, that would be 3 pi over 4, because you always measure from 0 to pi going in that direction. So the complex number here would be pi, yeah? Whereas it goes from 0 to minus pi down on the bottom, and so this would be minus pi over 2, and if you go right the way around, it's minus pi. I don't know why we didn't just go 0 to 2 pi all the way around by convention. You can do that, it works, all the maths works. If you go from 0 to 2 pi, it works perfectly, but just by convention for modulus argument form, a bit like in standard form, the first number has to be between 1 and 10. Well, in modulus argument form, we always take the argument, we tend to take the argument to be between minus pi and pi for all arguments. Yeah, minus pi is less than arg z, which is less than or equal to pi. That's the way we just tend to do it. It's just a convention, really. But yeah, those two facts are really, really important. I'd quite like to prove them to you and then maybe show you just one question. But yeah, let's have a look. Let's see what we can do. They do prove them in the book. I'm not really going to do it in a massively different way or anything like that. So let's let Z1 equal, well, we're going to write it in modulus argument form, R1 cos theta 1 plus I sine theta 1. Yeah, so I'm saying Z1 is, oh yeah, hang on a second. So I'm saying basically Z1 has a modulus of R1 and an argument of theta 1, and Z2, well, it would be sensible to make that R2 cos theta 2 plus I sine theta 2. Okay, let's see what happens when we work out what Z1 times Z2 is. We're going to have to times these together. Well, straight away I can write R1, R2 because they're going to get multiplied together. But then I'm going to have cos theta 1 plus I sine theta 1 multiplied by cos theta 2 plus I sine theta 2. All well and good so far. What I'm now going to try and do is multiply out that the trig basically, and we're going to need a lot of trig here, and that's the thing. Complex numbers has a lot of trigonometry in it. Oh yes, it does. Okay, so we get cos theta 1 theta 2, cos theta 1, sorry, cos theta 2. I said that wrong. trying to put that in a bracket, but it doesn't really matter, I guess. And then we're going to have, now if you think about it, we try and do this relatively quickly. In fact, let's do the real parts first. So I've done that one times that one. I've done the causes times together. Yeah, it might be useful to do this kind of lips and eyes stuff. When you do I sine theta 1 and I sine theta 2, the I squared is going to make -1, isn't it? So it's going to be minus sine theta 1, sine theta 2. And then we're going to have the imaginary components where you do like that times that and that times that. And that's going to be plus I times, and then I'm going to just put it in a new bracket. We're going to have sine theta 1 cos theta 2. And then we're going to have, and you need lots of space here for this, the other way round, sine theta 2 cos theta 1. Cool. And now it's about tidying up. So we're still going to have R1, R2. Now that looks very, very much like we could use the compound angle formulae for cos, and cos A cos B minus sine A sine B. Think of the little board in my classroom. It's all on there. That equals cos of theta 1 plus theta 2. Yeah? Remember, it works back to front for the minus with the cos. And then you're going to have plus I sine. Well, this is going to be theta 1 plus theta 2, isn't it? Okay, so we take a look back at this, yeah? And we think, well, what is this? This is simply going to be, if we look at Z1, Z2, this is now in a form which is the modulus argument form. So what is the modulus of Z1, Z2? Well, it's simply the number before the cos of stuff plus I sine of stuff. And so it equals R1, R2. If you like, you could actually do it the long way and work. You know, I can prove to you that that's definitely got a modulus of that. Because how do we work out the modulus of something? Well, we're going to actually, basically have to square it and square root it, if you know what I mean. And that's where you're going to get the cos squared plus sine squared is 1. But yeah, this is definitely going to have a length of R1, R2 if we look for the size of that. And the argument of Z1, Z2. Well, we can just look at the argument here. We can see it there. There it is. There it is. That's the argument of this complex number. It's just theta 1 plus theta 2. And that equals the argument of Z1 plus the argument of Z2. Yeah? I suppose I should make that clear that that is simply the size of Z1 times the size of Z2. So really, I can do that in, very few lines of working. It's just one quick trig identity that I'm using there. I'm not sure why they've made such a fuss of working it out in the thing. They seem to have made that look more difficult than it needs to be. With the subtraction, it's going to work very similarly as well. The division, with the division, it's going to be a little bit more awkward because we need to do the converting a complex number. When you've got an imaginary denominator, we need to realize the denominator. So it is a little bit tougher with division, but it works very, very similar. It really does. But that means that we can do some really cool stuff with this. If the complex numbers are in modulus argument form, we can times them together really quickly. So to give you a quick example, and I'm going to do a difficult one. Yeah, so I'm going to do, I think it's like D where it gets more difficult on the exercise 2D. Question 3D, it starts to get a bit more difficult. So let's say express the following in x plus iy form. Yeah, so I'm going to try and do this as quickly as possible. We've got root 6 cos pi over 3. Oh, not plus, but minus, because I'm doing a difficult one. Minus I sine pi over 3. And then I'm going to times that by root 3. And then I've got cos pi over 3 plus I sine pi over 3. Now, I wanted to pick a slightly more awkward one first, like this, because it brings up something else which is worth mentioning. Now, if both these complex numbers, and we've got two complex numbers here, if this was a plus here, this would be easy. We'd just have to multiply the moduli together, and we just have to sum the arguments, yeah? So it'd just be root 6 times root 3, right, root 18, cool, and it would be pi over 3 plus pi over 3, cool. Why can't we do that yet? Because that's a minus, so it's not completely in modulus argument form. But there is a very handy trick. You see, with cos and sine, and this is also on my board, think back to my classroom, sine of minus sine of x is sine of minus x. Yeah? And cos of minus x, well, that's just cos x. You can always use these two really handy trig identities to sort these things out so that they do end up being entirely in modulus argument form. So what am I going to do? I'm going to change this one. I'm going to leave it. I want those to be the same thing. So I'm going to make this one cos of minus pi over 3, because that's the same as cos over pi over 3. And then I'll make this one plus I sine of minus pi over 3 multiplied by root 3 cos of pi over 3 plus I sine of pi over 3. And now I'm happy because, okay, I've got two different complex numbers, but this is at least in nice modulus argument form. Yeah, I've got it exactly as I want it. And so what I can do now is simply sum the arguments, do R1 times, multiply the moduli, do R1 times R2 is root 18. Sum the arguments, theta 1 plus theta 2, well, that's going to be 0. And so I can tell you straight away that the answer to this is going to be root 18. That's it. In x plus iy form, that is simply root 18, or if you like, plus 0i. Yeah, and you can work that out and see if your answer is correct. And I believe your calculator has a complex number function. Try your complex number function on your calculator. See if you can get the hang of that as well, because that will be handy. That will be really, really handy. Just to show you that it is the same, though, I suppose we could have done it the long way round. Let's say we do it the long way round. Long way. I just want to show you that it does work, really. That was root 6, and then cos of pi over 3 is a half. Sine of pi over 3 is minus root 3 over 2i. And then we're timesing that by root 3. Cos of pi over 3 is a half, plus root 3 over 2i. Well, we could do root 6 times root 3, which is root 18. Yeah. And then this is like difference of two squares, isn't it? You're going to do a half times a half is a quarter. Like, then you're going to have minus a half root 3 over 2i, but then you're going to have plus a half times root 3 over 2i. They're going to cancel. And then you're going to have minus 3/4 I squared, yeah? Which becomes root 18 plus, a quarter plus 3/4, which is root 18. And there we go. That's why it ends up being root 18. That's the long way, but you'll probably understand that way a bit more. But try and get this brilliant technique of summing the arguments when you multiply two complex numbers together and multiplying the moduli. It's really, really, really useful. I hope that's been helpful. Please, though, get in touch with me if you want me to look at any weird questions from this exercise, maybe question 5 in exercise 2D. And let me know and I'll try and help. Okay, keep up the hard work and bye-bye.